In this video, we're going to look at how to predict the products of some common reaction types. The first type that we're going to look at are combination or synthesis reactions. It has two different names. You're going to be able to recognize a combination reaction from just the reactants because I will only ever expect you to predict the products of a combination reaction that's just two elements. So if you'll notice, looking at all three of these examples, element plus element, element plus element, element plus element. So you're going to recognize a combination reaction when it's two elements. When we looked at synthesis or combination reactions earlier in the week, we realized that they're called this because the two elements are going to combine to form a compound. Most students, when they start these types of problems, will just try to write the product by simply combining the two elements that are in the product. That is not correct. So that is not how you're going to think about this. Instead, when you're making a compound, you figure out the formula of the compound by thinking about the charges of the elements that make up that compound. So the charges in an ionic compound have to add up to 0. So off to the side, I'm going to think about, in this case, we've got beryllium. It has a +2 charge based on its location on the periodic table. Oxygen has a -2 charge. So here, the product will be BeO, because I need one of each of those elements in order to get the total charge of 0. After I figure out the formula based on compound formula ideas that we already know, then and only then can I balance this chemical equation. So it will be 2 berylliums, I'll put a 2 over here, and the O2, the oxygen, will keep its 1. I'll do one more combination example. I'm going to skip the second one and move on to the third one. Again, you have to figure out the formula of the product based on charges. So aluminum has a +3 charge. Fluorine has a -1 charge. So I'm going to need to get a total charge of 0. I'm going to need 3 fluorine ions, each with a -1 charge, with 1 aluminum. So that formula will be AlF3. Once I've figured out the formula of the product, then I can balance my chemical equation. I'm going to put a 3 here and a 2 here to get the fluorines matched up, and that'll make my coefficient in front of the aluminum a 2. So that's combination reactions. Let's move on to the next type. The second reaction pattern that we've learned are decomposition reactions. The easiest way to recognize a decomposition reaction just based off of its reactants is that it's going to be a single reactant. A single reactant. This is probably the easiest products to predict. You just take the compound that you're starting with and break it into the usually two elements that it's made up of. So for example, hydrogen iodide is going to decompose into hydrogen and iodine, and the only question you have to ask yourself about elements is it one of our 7 diatomic molecules or not? In this case, hydrogen and oxygen, or hydrogen and iodine, are both on our diatomic list. So instead of H and I, it's H2 and I2. Aluminum nitride is going to break down into aluminum and nitrogen. And again, I've got to ask myself if either of those elements are diatomic. Aluminum is not, so it'll just be Al. Nitrogen is one of our 7 diatomic molecules, so it will be N2. That's all there is to decomposition reaction patterns. The third reaction pattern that we learned about were single replacement reactions. These you're going to recognize because the reactants, there's always one compound with one element. Here we also have one element and one compound. So there's always an element and a compound. So when we figure out the product, the trick on single replacement reactions is that a metal or hydrogen always replaces the metal in the compound, but if the element is a nonmetal, it's going to replace the nonmetal in the compound. So whatever type of element that you have by itself, it's going to replace the same type of element in the compound. You also need to, again, when you're writing an ionic compound, make sure the charges add up to 0 for the product. And you'll notice I changed the wording on the note to say the charges add up to 0 for the products. So let's look at this first example. In the first example, we've got fluorine as our element by itself. Fluorine is a nonmetal. That means fluorine is going to take the place of the nonmetal that's in the compound. In our compound, sodium chloride, chlorine is our nonmetal. So those two are what's going to switch places. Chlorine and fluorine are going to trade. So when we get the products, chlorine is going to be by itself, and sodium and fluorine are going to be grouped together. Once you've figured out the pairings, then we need to check the formulas of both products. Chlorine as an element is one of our diatomics, so it's not going to be Cl, it's going to be Cl2. For the other product, sodium fluoride, off to the side, I've got to check that the charges add up to 0. Sodium's charge is +1, fluorine's charge is -1. So we just need one sodium and one fluorine. Therefore, the formula as written, NaF, is correct. It does give us something with total charge of 0. Finally, now I'm going to change the coefficients to balance this. I'm going to put a 2 here and a 2 there, and that should balance that chemical equation. Looking at the second example, this time the element that's by itself is iron. Iron is a metal, so it's going to trade places with the metal in the compound, in this case lead. That's the trickiest thing about Sigma replacement reactions, is figuring out metals replace metals, nonmetals replace nonmetals. So I'm going to figure out what the products will be. Lead is now going to be by itself, and the iron will now be a part of the compound. Now, I'm not sure what the charge of the iron is. This example didn't give me a charge for iron when it's in the compound, so I'm just going to assume the iron will be +2 and it'll still be FeNO32. But if it was magnesium, for example, where I knew that the charge was +2, I would have to take that into account when writing the product formula. So when I balance this, it looks like actually it would be balanced with all 1s as the coefficients. So there's 2 examples with single replacement. Let's move on to the next type. The fourth pattern that we learned about is the double replacement reaction. You're going to recognize double replacement reactions because they always begin with 2 ionic compounds as the reactants. Much like in the single replacement reaction, with the double replacement reaction, you've got to make sure that the compounds at the end are still ionic compounds, that it's a metal paired with a nonmetal. So one way to think about it would be to think about the way you would think about foiling in algebra. The metal from one compound is going to be paired with the nonmetal from the other compound. The anion or the negative ion is going to be paired with the positive ion from the other compound. So you'll notice in the product now, the silver and the chlorine are together in silver chloride. The sodium and the nitrate are together in the sodium nitrate. You still have to make sure charges add up to 0. You still always write the metal first in the compound name and the nonmetal second. So again, in the second example, the potassium is going to get paired up at the end with the nitrate to make potassium nitrate. The barium is going to get paired up with the sulfate to make barium sulfate. We still have to worry too in the final product formulas about charges adding up to 0. So let's look at a few examples that have not yet been done for us. Alright, the first one, I'm going to use some color coding to help me. I've got the potassium from the metal from the first compound is going to be paired up with the, in this case, polyatomic ion from the second compound. So we've got potassium paired with the phosphate polyatomic ion. The other pairing that we have is hydrogen with OH. So our second product will be HOH, which is actually something you're probably pretty familiar with. You could just call it H2O. So we know that formula is right, the HOH or the water. We do need to check the signs of the product. I'm going to do my work kind of below here. Potassium has a +1 charge. The phosphate has a -3 charge. So to get the total charge to add up to 0, the formula for potassium phosphate will be K3. I'd need 3 potassiums and just 1 phosphate. Now I've got my formulas figured out. Last step is to balance. So to balance, I'm going to put a 3 here and a 3 there, and that should do it. Let's look at least one more example. The next one, we've got hydrogen from the first compound paired with nitrate from the second compound. So HNO3. And then my second pairing, I'll have chlorine from the first compound, silver from the second compound. So it'll be silver with chlorine. I need to check the charges to make sure that my formulas are correct. Hydrogen has a +1 charge. Nitrate, NO3, has a -1 charge. So that formula HNO3 is correct because the total charge is 0. Silver has a -1 charge. Silver has a +1 charge. Chlorine has a -1 charge, so AgCl is also the correct formula. And actually this one turns out that with all 1s as coefficients, it will be balanced as it is. Since this one's tough, I'll do one more example with you. We've got the metal from the first compound, the non-metal from the second compound, so it'll be calcium, and phosphate is the polyatomic ion. The second product is going to get the metal from the second compound, the non-metal from the first, so it'll be Na and Cl. Notice I'm not carrying forward that 3 subscript on the sodium. I'm not carrying forward the 2 subscript on the chlorine. I'm figuring out the subscripts in the new compounds based on their charges. So calcium has a +2 charge. The phosphate polyatomic ion has a -3 charge. So to get this total charge to be 0, this will be Ca3PO4 2. On the other hand, sodium has a +1 charge. Chlorine has a -1 charge. So I just need one of each, NaCl, to make that formula. Finally, I'm going to balance. Looks like to balance this, if I put a 3 there, and then a 6 there, because I've now got 6 chlorine, and a 2 there, I think that will do it. It is now balanced, 3, 2, 1, 6. The 5th pattern that we looked at was combustion reactions. The good thing is, when you find a combustion reaction and you need to predict the products, all combustion reactions have the exact same product. The product will always be water and CO2. You're going to recognize a combustion reaction because they are very specific. A combustion reaction should be fairly easy to recognize. It's a very specific pattern. It is always a hydrocarbon, which is a compound made of only hydrogen, carbon, and sometimes oxygen, and then the other reactant is always O2. And the products are really easy to predict. The products of a combustion reaction are always CO2 and water. Their trickiest part sometimes is balancing them, but the key here, once you get used to it, is you always save the O2 for very last. So to balance this here, it looks actually like we've got 2 hydrogen here, 2 there. We have 1, 2, 3, 4 on this side, but we only have 2 here. So that's that even-odd disagreement that I've talked about before. I'm going to try and fix that by doubling this. That'll double this and cause me to double this. Now I have 2 carbon on both sides. I have 4 hydrogen on both sides. On the reactant side, I've got 2 times 2, which is 4, plus 2 more oxygen, which is 6. Over here I have 8, plus 2, that actually is balanced as it is. So that's a few examples of how to predict the products for each of the 5 reaction patterns that we've discovered in class. If you need a little bit more practice, I'm going to make a second video with some examples mixed up.